be a bit different than all the hardware-related talks today. So this is mostly about software and operating systems. It's about my summer of code project that I could do this summer. Thanks to lowRISC, so I wanted to thank Alex Bradbury and the lowRISC crew for giving me this opportunity to work on such a cool project. And I also want to thank my official mentor, Justin Cormack. He gave me insightful feedback and was like always there for questions and stuff. But I also want to mention Antti, who invented those Rump kernels, and he was very supportive of me and pinged me in my research and so on. So I want to give a shout out to those two guys. So I'm going to talk about my project, but it's only an example of how you can use Rump kernels. So most of the talk will actually be focused on what are Rump kernels, how you can use them on the RISC-V system in my example, but also more general. So just to motivation. So as you know, the goal of lowRISC is to provide an open computing ecosystem. So we basically already have this like in operating systems. So we have like Linux or NetBSD. Because you don't know, NetBSD is a free and open source Unix system. Yeah, as you all saw today, there's like lots of flexible processors that you can download and reconfigure. And when it comes to peripherals, there are also a few projects. But what I wanted to do, or what we want to do in this project, is take some operating systems code and use it for devices. So the hardware platform that this project is based on are those Minion cores, which Alex mentioned already earlier this day. The basic idea is that they are small RISC-V cores, and the idea is that you offload I/O to those cores, right? So you implement actual device protocols in software. So the initial idea is like SPI or SD card and so on. So the goal of this project was to explore like what can we do on those Minion cores. And I have to say, when I started this project, the Minion core concept wasn't really more than this diagram. So by now it's already a bit clear, like it's going to be a whole system, and the core is now kind of, we now have a better idea how those will look like. When I started, I didn't really know how those cores would look like. So what I took away from the Minion core idea is basically I treated this as a small RISC-V core and see what I could do with this. So the software platform that this project is based on are Rump kernels. So Rump kernels are basically a container for drivers, or a framework for drivers. So they give you access to production quality drivers like file system drivers, network drivers, audio drivers, and so on. So the idea is that you can run them not just in the kernel, as you would usually do, but basically run them everywhere, like in user space, in virtual machines, even on bare metal. Or you can integrate them into your own system. The code is based in NetBSD. So yeah, really think about this like if you know file system in user space in Linux, this is really a similar project, but it's much more flexible. So project proposal, which was initially the initial idea was by my mentor Justin Cormack, was to basically use Rump kernels on those Minion cores to do the I/O preprocessing using those Rump drivers. So in this example, using the TCP IP stack of NetBSD to basically process Ethernet frames that come in through this like I/O thing. So I'm a computer scientist, so I think more about high-level stuff than most of you guys probably. So the idea is that the TCP IP is processed with the Minion core, and the application cores still run those traditional operating systems, but they can offload some work to the Minion cores. So I want to give a short introduction to Rump kernels now, and it's typically kind of hard to explain. So I'm first going to start off with what they are not. So they're not an operating system. So this is kind of a Unix-y operating system. You know, we have an application that runs in user space. The application invokes system calls. It wants something from the operating system. So if it wants to send a network packet, it issues a send system call, which is then processed by those various subsystems, right? And somehow at the end of this pipeline, the kernel talks to the hardware, basically gives it some commands, what takes it. So in Rump kernels, we get rid of some of this stuff. So in Rump kernels, there's no processes or no threading. There's no virtual memory management, so there's no code that deals with MMUs or paging or any of this. There's no privilege levels, so we don't need the separation between user space and kernel or user accounts and so on. And there's no interrupt handling in the Rump kernel either. So we basically get rid of all this stuff there. And what we end up with is a much smaller system that has the application and the kernel in the same process. So we got rid of this distinction, but we are still able to run those drivers. And the thing which enables this is really the architecture of the NetBSD kernel. It was re-engineered in the last couple of years to make those drivers work in such a scenario where we don't have all those processes and scheduling and so on. Of course, this Rump kernel is not really workable on its own, so it needs a host, and it talks to this host using this hypercall interface. This hypercall interface provides things like thread scheduling, it does the memory allocation, and it does I/O basically. And what you also see is that before this picture we had here the hardware platform. Now we run it on some host. The host can be whatever implements this interface. So it can be a user space. So this can be a Linux kernel. This can be JavaScript. There's actually an implementation that runs this thing in a browser. Or it can be bare metal. So really, the idea of Rump kernels is to get those drivers out of the kernel and use them wherever you want. So you can use them however you like to use them. So here's a few typical use case scenarios. So the first and initial application of Rump kernels, or the way how to run them, is in user space on top of a Unix-like system. In this example, we have the Rump kernel, right? It issues hypercall to talk to the host. And we have a client application that uses the Rump kernel. So an example of this is a commercial example of this is a CD-ROM mastering software that uses all those CD-ROM file systems like UDF and stuff. They run in the kernel, in this Rump kernel, and the client application can just access those file system drivers from NetBSD and basically put a nice GUI unit that the user can use it. Again, in this example, the client is aware that it is using a Rump kernel, so of course you need custom code. To further test this, or I should say, this is also how drivers are tested on NetBSD nowadays. So if the NetBSD project, they have some test frameworks, and they based on this model. However, this client code is still aware of the Rump kernel. So this is why they added this the second basic architecture, which again features client app. In this case, the client app is unmodified, so it's normal C code or anything. And it talks to libc. So any well-behaved C software talks to libc. It wants something from the operating system. But now we have this hijacking library, so it basically intercepts the libc calls and it forwards it to the Rump kernel. So really, if a client application, for example, wants to do a file operation, and we want this file operation to be handled by the file system in the Rump kernel, the system call is hijacked, and then forwarded over the network, so usually TCP/IP or Unix sockets, to the server. In this case, both run again on some Unix-like systems. And yeah, so this was basically the first way to run normal applications on top of Rump kernels. And the cool thing is, of course, if you have a kernel panic, you just restart the process. So this could be Firefox, this could be the Rump kernel. If your TCP/IP stack crashes, you just restart it, like not rebooting. The most recent addition to Rump kernels are unikernels. So realizing that this kind of hijacking isn't really always practical, we now have a modified libc. So this libc is aware of the Rump kernel, and instead of executing system calls, it talks to the Rump kernel itself. So the client application, again, it doesn't know that it is running on a Rump kernel, but really in this case there's really not much else running besides the application and the Rump kernel. So this is why it's called a unikernel. There's only one application. This allows you to take existing Unix software. If it doesn't do anything too fancy, if it processes or virtual memory, you can just take it, bake it into this application thing, and run it directly on hardware or on your favorite virtual machine. And the cool thing is that you're not really on hardware. You can also virtualize this in user space. So this is a separate project by my mentor. You can also basically test NetBSD binaries in the Linux user space this way. Now for the project, I basically took a look at those two implementations or those two architectures. So they're not the only ones. So basically, I came up with a new way how to do this kind of thing. What I took is basically this model. As you might can see, like this client-server thing really is a bit similar to the application core, Minion core thing. But of course, we don't want to have a whole Unix on the Minion core. We want to run it on bare metal. So, which is why I started taking this existing hypercon implementation for bare metal x86, and I ported it to RISC-V. Wasn't too much of a problem. Actually, the most trouble I was having with the HDIF interface. So this is really running in RISC-V M mode. So I basically implemented all the HDIF protocols myself because I didn't want to use a proxy kernel or anything. So we have the Rump kernel in the Minion core. It uses the TCP/IP stack in NetBSD, so you can just compile it in. To actually deal with the I/O, I wrote an Ethernet driver, which runs in the Rump kernel, and it talks to basically the Ethernet, which is really just a virtual network card based on a Linux stack device. So the idea here is that system calls come in. They are handled by a sysproxy server, which again, it already existed, but it was written for Unix systems. So I rewrote it to run on bare metal, or bare metal with 5 to be more precise, and to use some kind of serial console. So the existing implementation uses the network stack. Of course, I don't really want to depend on TCP/IP if I actually want to provide TCP/IP. So I rewrote this to use a serial protocol, and so this is how it looks on the application core. So this is basically the same setup as before. We have an unmodified user application, and if it wants to offload some TCP/IP, this is handled by this already existing lib hijack Rump kernel. So just to give you an example, so let's assume the user application wants to send something, wants to issue some HTTP request. This is hijacked by this Rump hijack library, which then is further sys to the Rump client and basically issues a request call to the Minion core. So we tell this, here's a send sys call, here's some data that does it, And the sysproxy server then forwards this command to the Rump kernel saying, yeah, here's a system call, I want to send a network packet, please do this. The next thing that the Rump kernel does is, yeah, okay, give me the data. Of course, the Minion core runs in a separate domain, so we need to copy the data over, which is also handled by this protocol. So we give it the send a request back, please give me the data I need to offload. So we send back the data, and once all the processing finished, the Ethernet driver, the Ethernet frame is assembled and it's put on the wire, and this is how we can offload TCP IP using Rump kernels. But you can see that this is really, like, there's nothing here specific to TCP IP. You could use this for a USB, you could use this for file system, whatever you want. Just to be clear, the user application only uses this for TCP IP, so this hijack library, you can configure it, which kind of system calls you want to forward, so you can tell it to forward specific files or specific paths, or just like all socket related stuff. So in case of a file system related call, the user application still talks to the link. So this is the general idea. The current implementation has few limitations, of course. So as I said in the beginning, this currently only runs in Spike because there weren't no Minion cores when I started. So to do this, I also wrote a version level card for Spike. I hope to upstream this soon. It's based on concept. It's really simple, but I think it could also be useful for running Linux on RISC-V inside Spike. So the idea is that Spike simulates the Minion core, and the host, which is my laptop, offloads TCP IP to Spike. So it's not the most efficient setup, but it was really more of a demonstration. So this brings me to the next point. Turns out that Rump kernels they're quite small, they're not that small. So we have to see whether this setup really would work on an actual Minion core. The system requirements, I don't have any hard numbers, but you need at least 8 megabytes of RAM, and also the code image itself is like 2 megabytes big, so it might be a bit too big for an embedded system. Yeah. But I haven't really optimized it, so we can see. Of course, I guess you all agree that the way this is implemented is really efficient. Here the idea that I'm having is that if you would implement this on actual hardware, you would probably want to use a DMA engine for copy in, copy out. The problem here, of course, is that those pointers that are copied in and copied out are virtual addresses. So you would need to have some kind of IUMMU. Or the other way would be that you would run the offload client in the kernel. And the kernel would translate the virtual address to the physical address. But yeah, that's future work. And code still needs to clean up, so it's not all upstream yet, but I'll work towards this. So yeah, this already brings me to the conclusions. A bit early, but still. So what I really want to stress is this example that I showed you is not the only way you can do this kind of system. You don't need to do TCP IP offloading if you don't want to. You don't need to even use this kind of complicated system called matching. You can write your own protocol. You could, for example, write a kernel module that does communication with the Minion core, and then it would work for like all kinds of applications, not only applications that depend on libc. Although I would argue that most applications should use libc, otherwise they should have a good reason on that. But that's a different discussion. And you don't even need to do offloading. So, as I mentioned, we have this kind of unikernel thing. Maybe if I go back. Yeah, my open office is doing strange things. Yeah, to do that. So this whole unikernel thing, you can run your own applications based on the hypervisor implementation I did. And the cool thing is, once we port NetBSD's libc to RISC-V, which is mostly done, but there's a view, but you don't need a full operating system, so you just have the bare minimum that you need. and it's usually just a few megabytes that you have when you create a unique kernel. And yeah, like as I said, the code is usable even if we don't end up using this kind of system on the Minion core. You can use the drivers I wrote, you can use the hypervisor implementation I wrote, you can reuse the Spike virtual devices I wrote. So I hope, even though this does not end up being used in production, that it still was somewhat useful. So yeah, check out Rump Kernels, they're really fun. It's probably not be the last thing I did using them. And if you want to stay in contact, please do not recommend. And yeah, this concludes my presentation. Thanks for listening.
Have you done any benchmarking for TCP?
No, I don't have any hard numbers, but it's slow. It's, yeah, the protocol is really not optimal, so I wouldn't expect more than a few megabytes per second.
What about just the Rump kernel?
I haven't tested that. I haven't tested it on just RISC-V without offloading. I know that on x86 the Rump kernel is a bit faster than NetBSD because it has less overhead, and it's about 10% slower than a Linux kernel, which is kind of good because the NetBSD TCP IP stack it's cool, it's good, but it's not as fast as Linux. So yeah, that's all I can say.
With relation to TCP offloading, you've given a fine demonstration of how you would offload a send operation. But I see more problems when you have to do a receive of a packet, because here the receiving of a packet is not initiated by LSoC. Could you tell me something about how you implemented this or handled this?
So let me see if I can go back. So really, it's not different than receive is handled in a normal kernel. So I told you that Rump kernels don't have interrupts. That's kind of true, but it doesn't mean that you cannot have an application still invoking the interrupt handler in Rump kernel. So what happens if you have a receive interrupt from Spike, from the HDIF thing, is that it will trigger the interrupt, and this will invoke into a call into the Rump kernel, telling it there's a new packet, please receive it. It's really just using the same code as it would use on the in a NetBSD kernel, and it basically buffers the packet until the client application calls the receive. Let's see call. I don't know how it would work if you had some other system where like you use signals to notify LSoC about this. But actually the sysproxy server can issue requests to the LSoC and tell it like there's a signal. So there's actually a special packet that the server can issue telling the LSoC like, here I have the signal for you, please handle it. Yeah, you have probably more insight in NetBSD than I do.
Yeah. But like how much of the code is say 2 megabyte code is really hard? How much is the initialization, special cases, or how much? Like you compare to say the spikes or these program counter.
I don't have any. I didn't really investigate where most of the code was spent. So the hypercalling implementation is really small. It's a few thousand lines of C code. And the driver is also really small. It's also just like 300 lines of code. And this thing here, I think most of the code is actually used by the TCP IP stack and all the rest that we need on that. But yeah, for me it was a summer of code projects and a research project, so I was not obliged to do any measurements, so I could do them, but yeah, I didn't really.
It would be good to see what's the
Yeah.
great words. That's where it goes. Yeah.
Cool. Is that it? All right. Thank you very much, Sebastian.